Hi guys, so I'm back again. Um, I've taken a short break from the last video. So today we're going to be talking about perceiving objects and scenes. So it's more about agnosia than prosopagnosia. That's the next one. Anyways, so in this one, we'll talk about perceiving objects and scenes. Okay, so in the last few lectures, you have been learning about visual perception. Understanding how people integrate and interpret simple visual features in order to recognize objects and scenes remains a real challenge for cognitive psychology. Psychologists have put forward various principles that might explain how people group simple elements such as lines and compute three-dimensional object structures. So this research is also informed by neuropsychology and the effects of scene context. So part one, Gestalt laws of perceptual organization. So before recognizing objects, we need to group together features such as edges or lines and decide which ones are part of objects. The Gestalt psychologists came up with several principles that would enable us to do this. So according to the law of proximity, features are grouped into an object if they are close to each other. The law of similarity dictates that similar features, like edges of the same color, are likely to belong to the same object. The law of good continuation groups items that follow a continuous smooth edge, and the law of common fate describes something for dynamic objects that move together. The law of closure describes the tendency to fill in gaps that would create a coherent shape. So, um, basically, these are like stuff that makes recognize how we recognize objects. So, if the things are close together, we're more likely to group them into the same object, into an object. Sorry. The law of similarity is that if they are similar to each other, they are likely to belong to the same object. So, like if that chair has four legs and that chair also has four legs, so they're both chairs, basically, right? So, law of good continuation is I'm not sure actually. I think like um if the line flows, then it flows. Okay, you can tell I really don't know my shit and my stuff. I mean, I don't know my stuff. So, the law of closure describes the tendency to fill in gaps. So, this is basically like imagine you have an incomplete triangle. Like, let's say you have the edges, only one line is not meeting, or like there's a gap between that triangle. So, your mind would just is instinctively just like complete that line. So that's how we perceive objects. So law ad praegerans, sorry, it's German. I don't know how to say anything. Is that of several geographically possible organization, your brain will choose the simplest and stablest shape. So it's just really about how a whole object is formed from simple parts. So the Gestaltists observed that the process of figure ground segregation, which is the main image that you see here, deciding which parts of an image are background, is crucial. The process by which this is done remains of interest. Um, One example is Viscera et al. In 2004, and detecting concavities may be particularly important. I don't like this, but okay. So, how does the visual system decide which is figure and which is ground, or um, which is face and which is faces? So, the smaller region is yeah. This is a different um figure than the one I have put here. So so I think what applies is convex regions are more likely to be figure. So when does the visual system decide? Yeah, basically, we don't know. um, is it visual stimulation, focal attention, object recognition? We don't know. So what we see as the figure affects the depth processing. And you have something called occlusion, where something is obscured because there's something in front of it. I think, oh, I am having much. Oh, that's the end of part one. What did we understand from that? Who knows? Ha! Oh my gosh! Oh no, I'm not feeling good anymore. I felt a bit better for the last one because that was fun. Now you talk about stuff, figure grounds. Like I don't care about it. Okay, I need to care about it because I don't. I'm not gonna do any of this stuff. Maybe I don't know if I will. I hope not. But it's never. It's always safe to learn about this stuff, anyways. So part two: models of object recognition. Even though humans do it effortlessly, object recognition is a hard problem because objects can be occluded. Oh, so that's what it is. You mean rotated and seen in many different situations. Marr, 1982, so this person is important, revolutionized scientific understanding of this process by drawing together research from mathematics, psychophysics, and artificial intelligence. So according to Marr's computational theory, object recognition entails a series of representations of the input images that become increasingly sophisticated. So first, edges and other components are detected in early vision, the primal sketch, or the primal sketch. Early vision is the primal sketch. Okay. Then the depth and relative position of the object surfaces are mapped out in the 2.5D sketch. Finally, this representation is processed further to produce a viewpoint-independent 3D sketch model, 3D sketch or model of the 3D structure of objects. To do so, concave regions are used to separate the objects into generalized cones or cylinders. These components, it is a principal axis. These components become a principal axis of elongation, which is necessary for a 3D sketch to proceed. So, this is basically saying how Marr's computational theory wants a computer to recognize objects. Okay, so this part I understand a bit because I do have a little bit of computer science background. Okay, not a little bit. My degree is computer science, and I almost did my degree thesis on facial recognition. But that part is super hard. Like I have to be a super good so I have to be like super good at AI and stuff. And like, nah, I'm not gonna learn that in a year. What? Okay, anyway. Plus on Facebook, like what the hell? Facebook's API is horrible. Like I don't know if it's horrible, but people say it's horrible to learn. It's not horrible to learn, but it's like hard. Anyway, so Biederman's 1987 recognition by components model is also a structural account of object recognition broken down into stages. Edges and concavities are used to detect non-accidental properties which both define an object and are visible from many different angles. Objects are then decomposed into a visual alphabet of 36 different geons, which are combined to define many of the objects we see. Yeah, so basically in Marr's, I think they do it like by line, and then they made it into cones and cylinders, and then you have 3D. But Biederman extended that one and do it by geons. I don't know how to describe geons. So non-accidental properties are properties that are always there, and I don't know what properties are there. Okay. So Warrington and Taylor says that principal axes are important because that's how you recognize stuff like viewpoint independent or viewpoint dependent. Hold on. Let me just read. So one issue with structural models is that they strive to be viewpoint independent, meaning that they produce representations of objects regardless of the viewpoints of the observer. Yeah, so yeah, the issue is like whether or not the computer can tell what this is by view, like based on the angle or like or not, So, however, modern theories have emphasized that objects are recognized differently depending on the view. Tar and Pasig 2007. For example, both real objects and 3D shapes learned in the laboratory are detected more slowly as they are rotated from their initial viewpoint. The challenge for the resulting models is to explain how we combine all the views of an object that we perceive into a coherent entity. Structural models also have difficulty explaining subtle distinctions within a category, and it is not clear that all objects can really be defined by cones or geons. So basically, you can recognize the object well even if you remove some of the lines, as long as the concavity, the curve positions are kept. And there are two separate viewpoint on whether or not views on whether or not um, they should be viewpoint independent or viewpoint dependent. So the ones who supported viewpoint independent, which means they can recognize regardless of viewpoint, is Marr and Biederman. But viewpoint dependent is Tar and Butholf. I don't know how to pronounce it. I'm so sorry. So okay, that's the end of part. So part two is basically just like how we recognize objects and how we like try to break it down to make computers recognize them. So it's either by Marr's theory, it's with cones and cylinders, and according to a principal axis of elongation. Then Biederman tried to extend it by using geons and focusing and detecting the non-accidental properties of the image. Okay, so part 3, visual agnosia. A, dress, a, yeah, a dramatic, sorry, it's 3 a.m. So, a dramatic demonstration of the difficulty and complexity of object recognition is the abilities of patients with visual agnosia. This rare disorder, which can result from stroke and other instances of brain damage, is defined as a profound deficit in recognizing objects by sight. This diagnosis is restricted to those patients whose problem cannot be explained by visual acuity, color vision, or any other low-level problem. It can also be distinguished from a general problem with semantic knowledge or naming by showing that participants can describe objects from memory or by other senses such as touch. So visual agnosia is not because of visual acuity loss or color vision. It's also not a problem with object knowledge. They still know what objects are. They can describe how the object looks from their memory. Um, and it's not a problem with naming these objects. So this is something that happens after brain damage. It's not a developmental thing so far, but prosopagnosia is, I think. Um, so they know how objects look like, but because of brain damage, they can't figure it out anymore. Usually with lesions on the temporal lobe, which is the ventral stream, which involves in recognizing these objects, right? Okay. So assessment is often made through responses to line drawings, and historically, a distinction is drawn between agnostics who cannot copy line drawings, suggesting that they have problems in perceiving visual features, um, problems with simple perception, and those who can, suggesting that vision is intact but has become disconnected from semantic concepts of the object. So, in reality, this distinction is imprecise, and agnostics show a range of abilities. Yeah. Humphreys and Ruddock, 1987, reported experiments with an integrative agnostic who showed especially poor performance when objects were overlapping. This may illustrate that the disorder is caused by an inability to group features into a full object. So you have two types of agnosics. So one is apperceptive, so where the deficit is in perceptual processing. Um, so they can't really they have problem with simple perception, like with the letter A, they can't really write letter A. And then with associative agnosia, uh, they can basically draw the object, but they can't really name it. I think that's about it. Yeah. Okay. So that's about it. uh, I think it's so. There's also another kind called integrative agnosia, where you can see individual features but you can't put them together. So how that works is basically uh an object is basically broken down but they can't like piece it together. So um yeah, stuff like that. Anyway, so part 4, scene perception. This is the last one, no worries. Natural scenes are usually made up of different objects. It is therefore surprising that people can recognize scene gist very quickly. Biederman et al. 1974 and Porter and Levi 1969. This recognition may be based on global features and not require constituent objects to be perceived. Phenomena such as change blindness demonstrate that scene representations may not be very detailed. Participants often fail to notice lot changes if their onset is mass. Rensink, 1997. Given that we are moving our eyes several times a second, this kind of disruption is happening all the time. I don't remember this part. Our memory for scenes is also affected by top-down or conceptual factors. For example, Introp, 1997, described boundary extension. When reproducing a scene from memory, observers tend to extend the boundaries and depict a scene zoomed out compared to the original. The reasons for this are not completely understood, but it is likely to be because of what we remember as the context of the objects in scene. It is clear that the object and scene recognition interact. In particular, we interpret what we see according to the context. Palmer, 1975, showed participants a picture of a scene, like the kitchen, followed by a briefly presented object. The object was recognized more often if consistent with the scene, like a loaf of bread. This is evidence that scene context can affect object perception and that object recognition is at least partly susceptible to top-down influences. Um, okay, so I remember this. So in the class, we had to, the lecturer showed us a scene of like a trash can, like, uh, in front of a fence and stuff. So then we had to draw it from memory like later in the lecture. So what most of us just draw is basically a zoomed out version of that picture. When because when we saw it back, it's like, wait a minute, is why what I drew is actually like zoomed out than what it is. So yeah, and then there's also another one where the lecturer kind of flashed the picture of the kitchen and like asked us what we saw. There was like a split second, like and like and we were asked what was in there. So I said sink because that's the thing I remember. I said sink and then I saw a window. Yeah. But I don't really understand a scene perception, like what they're trying to say here. So okay, that's about it. I'm getting tired, you guys. Ha! I have one more. One more.